Okay, let's go ahead and start with a warm-up. I would like you to sketch a possible graph for the function f that has the following properties. F of 4 exists, the limit as x approaches 4 of f of x exists, but the function is not continuous. Okay, go ahead and show your graph to a neighbor. Your graph should look maybe something like this. Here, the limit exists at 4. If your function value is somewhere else, then we have the function value exists, the limit exists, but this function is not continuous. Go ahead and press pause. Okay, so we're going to go ahead and learn our last lesson of Unit 1. Now notice how this is coming from section 3.5, so when you actually go to your book assignment today, you're going to be in chapter 3. So those of you who use the PDF book in Google Classroom, make sure you're going to the chapter 3. So we're going to talk about limits of infinity today. So the limit as x approaches infinity, or the limit as x approaches negative infinity. So let me just remind you that a horizontal asymptote is a line y equals c that our function is going to approach as we go towards infinity or negative infinity. Okay, and I know it's been a while since we've talked about horizontal asymptotes. You did it about 11 months ago, okay, in pre-calculus. But remember, it's okay, and I know this one doesn't, it's okay to cross the horizontal axis somewhere in the middle, but what's the horizontal asymptote, excuse me. But what's always going to happen is that our horizontal asymptotes towards infinity and negative infinity, our graph is going to approach them. Okay, so why do I really care about a horizontal asymptote? Well, that's going to help us today when we are talking about limits towards infinity. So I'm going to go ahead and take this same graph. Okay, limits at infinity are asking us to describe the end behavior of a function. Okay, limits towards infinity are asking us to describe the end behavior of a function. Okay. Well, if we have a rational graph, we can really just imagine where the horizontal asymptote is. So here is my rational graph. You can see that we have an asymptote at y equals 3. So when I ask you for the limit as x approaches negative infinity of this graph, as we go towards negative infinity, you can see that our graph is approaching the horizontal asymptote, which is at 3. Okay. If I ask you for the limit as x approaches positive infinity, I'm asking for the behavior towards the right of the graph as we continue to go towards infinity with our x values. Okay, so we know that our function is going to approach our horizontal asymptote, so our limit is going to be that horizontal asymptote. Okay, so all of the limits I'm going to ask you to do today are all going to be towards negative infinity or positive infinity. And all that really means is what's happening towards the left of your graph, so the end behavior towards the left, what's happening towards the end behavior towards the right for positive infinity. Okay. So let's start off with something that we worked a lot with in both Algebra 2 and Pre-Calculus. Polynomials, okay? You have something called the leading coefficient test, okay? And it gave you a couple of things that we knew about our function. First of all, if our polynomial had an odd degree, then we would know that our left and right had opposite behaviors. Okay, like that, okay? If we have an even degree function, then our left and right have the same behavior. Like that. Okay. Also, we need information about the leading coefficient. So we could have a positive leading coefficient or a negative leading coefficient, LC for leading coefficient. If our leading coefficient is positive, then we know the right is going to rise. But if our leading coefficient is negative, the right is going to fall. So between these two pieces of information, the leading coefficient test can tell us what's happening towards the right and towards the left of our graph. Okay? So if I ask you for an infinite limit of a polynomial, these are the things that we need to think about. Okay, so I have some pretty basic examples here. Okay, go ahead and write these down. Okay, so since I'm asking for a limit towards infinity and negative infinity, I'm asking you for the left and the right behavior of the graph. Okay, we have an odd degree and a positive leading coefficient. So our positive leading coefficient means that towards the right, we're going to rise. And an odd degree means towards the left, it's going to have to be opposite. So towards infinity, our function is rising. And towards negative infinity, the left, our function is falling. Write this one down. Okay. I'm asking you for the limit towards infinity and negative infinity. So here I'm asking you for the right behavior, and here I'm asking you for the left behavior in terms of ending behavior, okay? So we have a polynomial, Our leading coefficient is positive, so we know our right is rising. And we know our degree is even, so the left has to have the same behavior. So, towards both infinity and negative infinity, our function is rising. Okay. Last basic example. We have a negative leading coefficient, which means the right is going to fall. And we have an even degree, which means the left is going to have the same behavior. So, when I ask you for the limit towards infinity, our right ending behavior is falling. When I ask you for the limit towards negative infinity, our left behavior is falling. Okay. Now I'm going to go ahead. Oh, there they are. I have two examples here. I want you to write them down. Maybe take a crack at what you think the answers are, and then we'll go through them together. Okay, so here I'm asking you for the right end behavior, and it looks like we have a positive leading coefficient of odd degree, so the right is going to be rising. Okay, now, with this second one, be careful because it's not in order. This is technically our first term because it's the highest degree. It has a negative leading coefficient and an even degree. So when I'm asking you for the limit towards negative infinity, I want the left end behavior, which is negative infinity. Okay, so be careful. Make sure your polynomial is in order. Okay, so a quick rule here. Don't write everything down. I'll highlight what I think you should write down. Okay, so two rules, they're basically the same thing, just one's towards infinity, one's towards negative infinity. If you have the limit towards infinity and you have a number over x to a power, that fraction's going to go to 0. Same thing with towards negative infinity. Okay. So basically what's happening is we have a constant in our numerator. Our denominator is a polynomial. Well, that's going to get bigger and bigger and bigger and bigger and bigger and bigger and bigger. And so our fraction is going to get smaller and smaller and smaller and smaller and smaller until we approach 0. So here's an example. Okay, so you've been trained to look at direct substitution. Well, if we plug infinity in, okay, we have 2 over approaching infinity. All right. Our rule says, well, 2 over approaching infinity, that fraction is going to go to 0, and we're left with 5 minus 0. Okay, now we're going to get into the fun stuff here. Go ahead and write this example down. All right, if we were to use direct substitution, our numerator goes to infinity and our denominator goes to infinity. This is what we call indeterminate form, which is also what 0 over 0 is. Okay, basically it's, we're stuck. But what your strategy is going to be when you have a rational towards infinity or negative infinity, okay, we can divide each term by the degree of the denominator. I'll show you what I mean. Our denominator has a degree of 1, so x to the first. So every single term in numerator and denominator is going to get divided by that degree of the denominator. Okay. We were looking for the degree of the denominator, and every term gets divided by that. All right. Well, look at what happens here. We can simplify 2x over x to 2, and we can simplify x over x to 2. Okay, well, what did we just talk about? If we have the limit as x approaches infinity or negative infinity of a number over x to a power, well, we know 1 over infinity, that's going to approach 0. And same for this guy too. So what we're left with is 2 over 1. Now, how many of you knew that that was going to be 2? And how did you know it was going to be 2? Okay, you don't have to do this every time. There will be some times where you'll need to, but if we have a straightforward rational like these right here, we can remember what our asymptote rules are. Okay, so I want you to go ahead. Let's start with this one right here. I know it's super pixelated, but I'm trying not to show the rest here. Okay, when I ask you for the limit towards infinity or negative infinity, then I'm asking you for, in a rational graph, the horizontal asymptote. So here we go, we're towards infinity, we have a rational graph, we have degrees that are the same. So if you remember, if our degrees are the same, our horizontal asymptote occurs at the coefficient. That saved us a little bit of work, huh? If the degrees are the same, then our horizontal asymptote is the leading coefficients. But I'm only identifying the horizontal asymptote because we have a limit towards infinity. Okay, go ahead and write this one down. we have a limit towards infinity, which means I'm asking you for the end behavior. Since we have a rational graph, then we can identify the horizontal asymptote and be good to go. Okay? Well, if we look at the degrees of the numerator and denominator, our denominator has a larger degree, which means our horizontal asymptote is at y equals 0. So this limit is going to be 0. If our denominator has a higher degree than the numerator, our horizontal asymptote is going to be 0, which means the limit towards infinity or negative infinity will be 0. Okay. The only time I guess not the only time, but one of the times these asymptote rules aren't really going to help us avoid some work. Okay, so far those two had a shortcut. Go ahead and write this one down. If you notice, we have a higher degree in the numerator. And if you recall back to pre-calculus, this means we have a slant asymptote. And when we have a slant asymptote, we're going to have increasing or decreasing behavior towards the right and the left. So we're actually going to have to do the work like we did in that first rational example. Okay, so what is the highest degree in our denominator? It's x to the first. So we are going to take everything and we are going to divide each term by x to the first power. Okay. All right, so what happens? We get 2x minus 4 over x over 1 plus 5 over x. So we know that towards infinity, 4 over x is going to go to 0 because it's a constant over x. So a constant over going towards infinity, the fraction is going to go to 0. Same thing with 5 over x. So what we're left with is the limit as x approaches negative infinity of 2x. All right, well, we can do that. That's polynomial. 2x is a line with positive slope, so towards the left, it's going to be falling. Okay, here we go. Last type of example. Okay, and we're gonna look at towards infinity and maybe just start towards negative infinity to see how it would be different. So this is a rational graph towards infinity. So yeah, we're still thinking about our asymptotes, but this radical is really throwing a kink in things. Okay, so instead of just thinking about where the horizontal asymptote is, we are going to have to think about the strategy of dividing by the degree of the denominator. Okay, this radical is throwing that off, so we're going to have to use that strategy. That's fine. Now, when we think of the degree of the denominator, we have the square root of 2x squared. So technically, the degree would be this, which is x as long as x is greater than 0. And since we're going towards infinity, then that's okay. All right. So basically, we are going to be dividing each term by x. So we have the limit as x approaches positive infinity. We have to divide each term by x, but in our radical, x is the same thing as x squared. Okay, so we have 3 minus 2 over x over radical 2 plus 1 over x squared. Okay, So towards infinity, remember we're talking about infinite limits. Towards infinity, a number over x is going to go to 0. Towards infinity, a number over x squared is going to go to 0. And we're left with 3 over radical 2. Okay. Now let's go ahead and talk about how it's different if we're going towards negative infinity, because it is. So once again, we're going towards infinity or negative infinity at this point. And we have our rational graph that's not as straightforward because of this radical. So we need to do our strategy of dividing by the denominator's degree. Well, we have the square root of x squared again. So the square root of x squared is actually not equal to x. Negative radical x squared is equal to x when our x's are negative, okay? Since we're going towards negative infinity, we're talking about negative x values. So the square root of x squared isn't x. We have to throw the negative on there to balance out these because these are negative numbers, okay? Well, so how is that going to affect our limit? So what we're going to have to do, since we are dividing each term by x, in our radical, we have to divide by x squared, but the square root of x squared isn't the same as x, so we have to counteract that with this negative because of this right here. So our process is going to be the same as before, but we had to adjust with that negative. So these go to 0 just like they did before, but now we're left with 3 over negative radical 2. Okay, I'm probably out of time to show you, but I really would encourage you to graph this rational equation. What's happening is we have two horizontal asymptotes. Towards infinity, it's approaching this. Towards negative infinity, we're approaching this number. Okay,